Okay, so the diagram shows a sign, okay, attached at point A. It's supported by two light rods, AB and AC. So AC, it says, is horizontal, okay, and the rod AB here is inclined at an angle alpha to the horizontal. So it's on an angle, the rod AB, that angle alpha there to the horizontal. And it says sine alpha is 0.6. So then we have the mass of the sign is 12 kilograms. Okay, so we can then establish the weight of this sign then, of course, will be 12g. And then it asks for the thrust in the rod, calculate the thrust in the rod AB and tension in rod AC. Now, of course, we're familiar with the term tension, okay, in AC. So maybe we'll put tension going that way there, yeah, because it is literally holding that sign up, isn't it? Okay, tension in that rod there is making sure this is in place. Now, the reason why AB has got a thrust instead of a tension is because if you think of the purpose of this rod here, it's not a force which is pulling away like AC is, isn't it? That's sort of like pulling away to hold this sign in place. This rod is actually pushing, yeah? So instead of it being a tension, we call it a thrust. So we call it T2, but it's actually pushing at A, isn't it? To keep it in place. Now, you can just imagine what would happen if you take away this rod. Okay, what would happen if you take away this rod? Well, of course, the whole sign would probably collapse, wouldn't it? Yeah, there wouldn't be a balance, it would just collapse. So the purpose of this rod here is to push and hold that in place here, okay, so that it doesn't fall. So we're actually pushing towards A, that's why it's called a thrust. But we deal with it just like we would as a tension, okay, so we call that T1 there and we call this T2. And of course, the idea then is to resolve the forces, okay, in the X and Y direction, okay. And one thing that is important, we sort of get to grips with this is that the force is acting on a point, and this would be the point here, point A. Now we know, of course, 12G is acting vertically downwards, okay, the weight of the sign. Now, and of course then T1 is going to the left, so that's quite straightforward there. The issue with T2 is that it's acting towards the point of equilibrium here, okay, so it's pushing towards it. And you notice with our force diagram, with the cross situation, all the forces must act away, okay, away from the point. But here we've got the issue, isn't it, that this thrust is sort of pushing towards it. Now we can't have like an arrow going inwards, okay, in terms of resolving forces, okay. What we need to do is look at this thrust here and appreciate if it's pushing in this direction, we could sort of follow that push all the way through the other side of the point, okay? So we could imagine, okay, and it is just imagining it, that thrust, the whole effect of that push will be pushing in that direction here. And then if we see the push from the other side, the other viewpoint, in terms of the direction it's going in, we can then see the thrust going away from point A. Okay, we can see it like that. So the effect of it is pushing in that direction. So let's have it going away from A, and actually the effect of it is going in that direction there. So we have T2 going that way. So then you can think of it then like as a normal tension, can't you? You could consider it as a tension. And the other thing as well important then, just with the geometry, if I draw a line going across here, that angle alpha there will be the same then as this angle alpha here. Okay, opposite angles. Two straight lines across are equal. So the T2 will be going in this direction, the thrust is pushing in this direction, and when we resolve it then to the X direction containing the angle, it will be T2 cos alpha, and then the opposite then it'll be T2 sine alpha. And quite simply then what we get is, when we resolve, okay, because the forces are in equilibrium, well, we can say that T2 sine alpha is equal to 12G, okay, yeah, when we resolve in the vertical direction. So T2 sine alpha is equal to the weight, and of course then we know sine alpha is 0.6 because they've given us that. And then straight away then you can work out T2, the thrust, which is what they're asking for in part A, by doing 12 times 9.8. So 12G is, divide them by the 0.6. So I do that on my calculator, I get 196 newtons. So I've got my thrust. The next thing then is to work out what T1 is, the tension. So when we resolve then a horizontal direction, okay, we can say then quite simply that T1 is equal to T2 cos alpha. Okay, that will balance this. Now I know, of course, that T2 is 196. I just need to work out cos alpha. Now, they don't tell me what cos alpha is, but they do tell me what sine alpha is. They've said, haven't they, that sine alpha is 0.6. Now what we can use then, we can use the rule, can't we, that sine squared alpha plus cos squared alpha is equal to 1. Okay, so then I've got 0.6 then squared, would be square sine alpha, plus cos squared alpha is 1. So then cos squared alpha will be 1 take away 0.6 squared. And to get cos alpha then, we just square root, take the positive, and we get then the answer then for cos alpha. So if I do square root 1, take away 0.6 squared, and I get that then 0.8. Okay, so in my answer then for T1, it'll be 196 times 0.8. So I work that out on my calculator, and I get 156.8 newtons.